Hello everyone and welcome to another IB Physics video. Today we'll be looking at a paper 2 exam from May 2022, Timezone 2. So let's get started. In this first question, it says that airboats are used for transport across a river. To move the boat forward, the air is propelled from the back of the boat by a fan blade. And you can see there is a fan and it pushes the air back. An airboat has a fan blade of radius 1.8 meters. The fan can propel air with a maximum speed relative to the boat of 20 meters per second. The density of air is 1.2 kilograms per cubic meter. Outline why a force acts on the airboat due to the fan blade. This is a 3-point question. Now, it's a why question, so you don't have to actually calculate anything for now. But here's the first thing. The fan blade pushes the air back. Now, when you say push, you should actually say applies a force on the air. So let's open up the space here. Towards the back or backwards. Number 2, according to Newton's third law, so you mentioned something about Newton's third law. The air applies a force forward on the fan blades. And you should probably mention something about it being an equal and opposite force. There are other alternative answers for this question, and you can also say that the air gains momentum backwards. The conservation momentum means that there's going to be a forward impulse on the boat, and the force is the rate of change of momentum. Either using the Newton's third law or the change of momentum are both acceptable. In part B of this question, it says that in a test, the airboat is tied to the riverbank with a rope normal to the bank. The fan propels the air at its maximum speed. There is no wind. Number 1, show that the mass of air that moves past the fan every second is 240 kilograms. So, first of all, we have to find mass. Earlier in the problem, you're giving density. So density is equal to the mass over the volume. And this tells you that the mass is equal to the density, let's call it rho, times the volume of the air. Now, how do you find the volume? The air that moves through the fan creates a cylinder shape as it moves past, like so. You have the base, the area of the fan, and when you multiply this by the length or the distance the air traveled, you get the volume. So this is density is equal to the area of the fan times the distance traveled, L, by the air. Well, the air has a velocity. This distance that it travels is the velocity times time. So let's remove that and put velocity times change in time. And finally, that is it. There's nothing else we can do. The mass is equal to, we will find the density. If you go back up into the question, density of the air is given as 1.2 kilograms per meter cubed, the fan radius as 1.8, and the velocity of the air as 20. So going back down, the mass of the air is 1.2 kilograms per cubic meter, multiplied by the area, which is pi, radius, which is 1.8 meters squared, times the velocity of the air, which is 20 meters per second. And this gives us approximately 244 kilograms per second, which is one more significant figure than given, so that's the answer. In part 2 of this question, it says, show that the tension in the rope is about 5 kilonewtons. We're going to use the equation where the force equals the change in momentum over the change in time, which would be equal to the mass of the air times the velocity of the air over the change in time. Now, the change in time in this case is, of course, 1 second. Or you can say the change of the mass of the air per unit time, which is kilograms per second. So we use 244 kilograms per second for this value here, times the velocity of the air, which is 20 meters per second. And we get approximately 4,900 or 4.9 kilonewtons, which is close enough to 5 as required. For part C of this question, the rope is untied and the airboat moves away from the bank. The variation with time t of the speed v of the airboat is shown for the motion. So this is the graph, and you can find this graph that it has velocity in the y-axis and time in the x-axis. Part 1, it asks us to explain why the airboat has a maximum speed under these conditions. Well, one of the parts of this question says that the speed of the air being pushed back is always the same. So the force will also always be the same. But what actually happens is, as it goes faster and faster, air resistance increases. So we call these resistive forces. Which you can call air resistance. Increases with velocity. Which means at a certain velocity, the net force will be 0 and the acceleration will be 0. And this means it cannot move faster than this maximum velocity. For part 2 of this question, it asks us to estimate the distance the airboat travels to reach its maximum speed. First, we're going to use the area of the graph, so let's write that down. Remember that if you don't write what your method is, it's hard for the other person to know what you did. So don't just write a random number there, write what you did to find this actual value here. So you have the velocity and time graph, which means the area is the displacement. Now, assume that maximum velocity will go up to 18, so it's a full graph. If you see one of these squares, it has a base of 5 seconds and a height of 2 meters per second. So each one of these squares is equal to 10 meters. If you count them up, the first column here will have about 9. The second column will have also about 9. Let's say the third column will have about 8. This was also about 8. Let's say this is about 7 squares. Let's say this is about 6 squares. Let's say this is about 4 squares. And we can think of this as maybe just 1 square, a little bit more than 1. So let's add them all up. We have 1 plus 5 is 5, plus 6 is 11, plus 7 is 18, plus 8 is 26, plus another 8 is 34, plus 9 is 43, plus another 9 is 52. So there's approximately 52 of these squares. So it's 520 meters. Now, you have a very wide range because you're just estimating. If you do not count the squares that were cut off, you would get something around 480 meters. If you count all the squares that were cut off and just round up, you get about 560 meters. So just try to do your best. Notice this is approximately about the middle of the range, so you should be all right with that. Part 3, it says deduce the mass of the airboat. What you can do is you can get the force. We know the force. We have is equal to the mass times acceleration. So in order to find the acceleration, you have to get the force per mass. Sorry, to get the mass, you need the force over the acceleration. Now, how do you find the acceleration? Well, you go back to this graph again, and you want to find the initial acceleration here. So, if you were to use the origin and this point here, this is 2 meters per second over, and this is 2 seconds, which is approximately 1 meter per second. Squared acceleration. So let's go back down. You say using the graph, the initial acceleration A is equal to 1 meter per second squared. So you have the mass, which is equal to 4,900 newtons, which is the force we previously calculated, divided by 1 meter per second squared, gives us just 4,900 kilograms. In part 2, or question number 2, a fixed mass of an ideal gas is contained in a cylinder closed with a frictionless piston. The volume of the gas is 2.5 times 10 to the negative 3 cubic meters when the temperature of the gas is 37 degrees Celsius. And the pressure of the gas is 4 times 10 to the 5 pascals. A, calculate the number of gas particles in the cylinder. So first of all, this is in Celsius, which means you need to convert it into Kelvin, which would be around 310 Kelvin. Next, you might be used to using PV equals nRT. But this just means when you find the moles, you have to convert into number of molecules by using the equation that the number of molecules is N, the number of moles times Avogadro's number. Instead of using this extra step, you should probably remember that this same equation, PV, equals the number of molecules times the Boltzmann constant times the temperature, NKBT. The reason you use the gas constant R in this equation is because you want to get the units in moles for the number of atoms. Using the Boltzmann constant gives you the number of atoms in just number of atoms, not moles. So you should use this equation here, which makes it easier to calculate that the number of atoms would be the pressure times the volume over the Boltzmann constant times the temperature. And using these values, you should get 2.3 times 10 to the 23. If you find the number of moles first in this, you should still get the same final answer. In part B of this question, energy is now supplied to the gas and the piston moves to allow the gas to expand. The temperature is held constant. Discuss for this process the changes that occur in number one, the density of the gas. So, number one, the volume increases. And the number of atoms or particles remains constant. Which is related to the mass, right? Therefore, the density we use rho for the density, which is the mass over the volume, decreases. Part two, what about the internal energy of the gas? First, the temperature is held constant, which means the internal energy is constant. Now let me show you why. The internal energy, which you call U, is the total kinetic energy plus the total intermolecular potential energy. But this for ideal gases is zero. And the kinetic energy, on average, is only proportional to the temperature. If the temperature is the same, kinetic energy is the same, which means internal energy is also the same. For number three, a loudspeaker emits sound waves of frequency f towards a metal plate that reflects the waves, and then there's a small microphone here, and this microphone is moved along the line from the metal plate to the loudspeaker. The intensity of sound detected at the microphone as it moves varies regularly between maximums and minimum values. The speed of sound in air is 340 meters per second. Part A, number one, says explain the variation in intensity. If there's a variation in intensity, it has maximums and minimums, it must be interfering in some way. So, what is interfering? Well, you have an incident wave and a reflected wave. So, the wave incident interferes or superimposes with the reflected wave. And this is exactly the definition of a standing wave. So you create a standing wave. Because if you remember, a standing wave is created when there are two waves moving in opposite directions. So this standing wave has nodes and antinodes, but what is actually important is at the nodes, the waves destructively interfere, so the sound or intensity is lower. So it means lower intensity or volume. And at the antinodes, you have maximum intensity because it's constructive interference. So at antinodes, constructive, so it's louder or higher intensity. In part 2, adjacent minima are separated by a distance of 0.12 meters. It asks us to calculate the frequency. So you have node, a node, this would be where the minima occur, and they're separated by 0.12 meters, which means the wavelength is twice this size. So this is 1/2 the wavelength is equal to 0.12 meters. This means the actual wavelength is 0.24 meters. You don't actually have to draw it for the answer. It's just for the benefit of the students that are watching this. The frequency is the velocity of the wave over the wavelength. The velocity is stated to be 340 meters per second. The wavelength is 0.24 meters, which means the frequency must be approximately 1,400 hertz if you round to two significant figures. Part B. The metal plate is replaced by a wooden plate that reflects a lower intensity sound wave than the metal plate. State and explain the differences between the sound intensities detected by the same microphone compared to the sound intensities detected when it has a metal plate. Okay, so first of all, if you have a wooden plate, the reflected waves have smaller amplitudes, right? Number one, waves reflected by the wooden plate have lower amplitudes. And the reason for this is because the intensity is proportional to the amplitude squared. Lower intensity means lower amplitude. So what happens then? The maxima will make the amplitudes add up, but if you add something smaller, you have a smaller maxima, right? Which leads to a lower maximum intensity. What about the minima? Well, during the minima, if they had the same amplitude, it would be subtraction, so you have an amplitude of 0. But if you lower one of the amplitudes and they have destructive interference, you don't get all the way back to 0. You have higher amplitudes, which means higher intensity. This will not change the position of the maximum or the minimum, so they are at the same positions. All that will happen is the maxima will be lower and the minimum will be higher. Question number 4. It says, identify the laws of conservation that are represented by Kirchhoff's circuit laws. There is a current law and there is a voltage law. The current law is due to the conservation of charge. And the Kirchhoff voltage law, well, voltage is related to energy, so it's related to the conservation of energy. And to be honest, there's not a lot of conservation laws related to this. You have the conservation of charge, conservation of energy. Some of the laws that are not actually part of the Kirchhoff's laws, but they're still there, is the conservation of momentum, which is not applicable. And the only other conservation laws that you probably know of are for the particles, baryons, leptons, and so on, which also are not applicable in this case. So, in this following question, it says that a cell is connected to an ideal voltmeter, a switch S, and a resistor R. The resistance of R is 4 ohms. And it also says that when S is open, the reading in the voltmeter is 12 volts. Then when S is closed, the voltmeter reading is 8 volts. Part 1, state the EMF of the cell. Well, quite simply, if you have the EMF as being equal to the terminal voltage plus IR, the terminal voltage is what's being read by the voltmeter, but when it's open, the current is 0. So you still just get that the EMF is whatever the voltmeter tells you it is. So in this case, the voltmeter or the EMF is simply 12 volts. In part 2, it says deduce the internal resistance of the cell. Well, you have the equation again. EMF is equal to the terminal voltage plus the current times the internal resistance. Now, the second part, we know this is 12 volts. In this case, we have the terminal voltage as being 8 volts plus IR. All we have to do is we have to find the current. Well, we know that the voltage drop is 8 volts. So the current must be the voltage drop over the resistance, in this case 8 volts over 4 ohms, which is 2 amperes. This equation for Ohm's law is applicable to any independent resistor. So current is 2 amperes, which means current times internal resistance is equal to 4 volts. The current is 2 amperes, internal resistance is 2 ohms. And if you use correct number significant figures, it would be 2.0. Part C. The voltmeter is used in another circuit that contains 2 secondary cells. Cell A has an EMF of 10 volts and an internal resistance of 1 ohms. Cell B has an EMF of 4 volts and an internal resistance of 2 ohms. Calculate the reading in the voltmeter. So, in order to calculate the reading in the voltmeter, you have to use Kirchhoff's law. So, first of all, ignore the voltmeter as part of the circuit. You're just going to go around it. So we have current I. The whole circuit has the same current, so we're just going to use one of the I's. And we can use this path. So, according to this path, we have plus 10 volts times, or minus, the current times 1 ohms, which is 1. Now here, it's going through the second battery in the opposite direction, so it's minus 4 volts. But it's still also minus the current times 2 ohms, which is 2. And that's the end of the circuit, so equals 0. So what we have to do is you have to find, first of all, what the current is. Using this, all of these values, you can find that the current is just going to be simply 2 amperes. Now to find the voltage difference, we use this resistor and this EMF. So the terminal voltage would be the EMF minus IR. In this case, 10 volts minus 2 times 1 ohm, which is just 8 volts. If you use the same thing here, same thing, plus 4 EMF times 2 times 2, which is 4. You add them together, 8 volts. Part 2 of this question asks us to comment on the implications of this answer on cell B. So first of all, we'll go back to this diagram here, where we erase our notations. There is a current. The current is 2 amperes going through the circuit. Now, that means cell A is giving energy or power to other components of the circuit. So it's 10 volts and 2 amperes, so there's 20 watts going through this. Where is this energy going? Well, some of it goes to one of the internal resistances here, IR squared. So this would probably get I squared R, so it's 4 times 1 watts. This is 4 times 2, so it's 8 watts. And this is 2 times 10. There's 20 watts coming from the cell. That means 8 of these watts are going somewhere else. They're going into this other cell. Basically, you're using energy from cell A to recharge cell B. So, cell A is being used to recharge cell B. The only difference between cell B and a normal resistor is that the resistors normally would use that electromagnetic EMF and current and just convert the energy into heat or thermal energy, while cell B gets that energy and just stores it. Part D of this question says electricity can be generated using renewable resources. Part 1, outline why electricity is a secondary energy source. And of course, a secondary energy source is generated from other primary sources. Or you can also state that secondary energy sources are primary energy sources that have been processed in a form that is easier to use by other machines. 2. Some fuel sources are renewable. Outline what is meant by renewable. And this is just a one-point question, so there's a lot of different answers that can be used. So, number 1, it can be a type of fuel that can be replenished easily. Or you can also state that it is a fuel that is replaced faster than is consumed. Or you can also say that it's a type of fuel that will never run out, is basically limitless. You can also say that it's a fuel from renewable sources, such as biofuel, hydrogen, hydroelectric. Or you can also give other types of examples of renewable energies, geothermal, sunlight, etc. Okay. In E, Part 1, a fully charged cell of EMF 6.0 volts delivers a constant current of 5 amperes for a time of 0.25 hours until it is completely discharged. The cell is then recharged by a rectangular solar panel of dimensions 0.4 times 0.15 meters. At a place where the maximum intensity of sunlight is 380 watts per square meter. The overall efficiency of the recharging process is 18%. Calculate the minimum time required to fully recharge the cell. So, first we have to find the energy of the cell. The energy of the cell would be the power times the time, which is the voltage times the current times the time. In this case, the voltage is 6 volts times 5 amperes times the time of 0.25 hours times 60 minutes per hour times 60 seconds per minute. This gives us approximately 27,000 joules. Now, to see how long it takes to recharge, let's look at the available power. Which is the efficiency multiplied by the intensity of the sun and multiplied by the area. The efficiency is taken to be 18%, so 0.18, times the intensity of 380 watts per square meter, and times the area of 0.4 times 0.15 meters. This gives us approximately 4.1 watts. So the time would be the amount of energy or work required divided by the power available. So it's 27,000 divided by 4.1, giving us approximately 6,600 seconds. Two significant figures. In part 2 of this question, it asks us to outline why research into solar cell technology is important to society. And it's a one-point question, and the answer or marking scheme literally says any coherent reason. So basically what you can say is, well, we need to improve efficiency because it's not polluting, because it's renewable. It will help us to reduce greenhouse gases. It will help us to reduce the use of fossil fuels. Anything like to those within those lines that it helps us to make this better and at the same time improves the environment by reducing pollution. Anything like that will give you the points. Question number 5. An experiment is carried out to determine the count rate corrected for background radiation when different thicknesses of copper are placed between a radioactive source and a detector. The graph shows the variation of corrected count rate with copper thickness. Outline how the count rate was corrected for background radiation. Well, this is just very simple. Background radiation is a systematic error. So the background count rate is subtracted from the readings. In part 2 of this question, it says, when a single piece of thin copper foil is placed between the source and the detector, the count rate is 810 counts per minute. The foil is replaced with one that has 3 times the thickness. Estimate the new count rate. So we will use the graph, and it says it's approximately 810 counts. So it must be somewhere around here, which we can estimate to be 0.25 millimeters. We go to 3 times that thickness up here, and it will be somewhere around 300 and let's say 80. So initial thickness is 0.25 millimeters. So using the graph, the count rate at a thickness equal to 0.75 millimeters is approximately 380 counts per minute. You don't have to get the exact reading 380 because it's a graph. You just estimate any number within a reasonable range will be counted as correct. Part C. Further results were obtained in this experiment with copper and lead absorbers. So you have copper at 3.5 and lead at 3.5 millimeters thickness. Comment on the radiation detected from this radioactive source. Remember, there's basically 3 types of radiation: alpha, beta, and gamma. Number 1, it is not alpha radiation. Because this would have been immediately stopped. And it's stopped by basically anything. Second, lead absorbs the radiation better. Third, you can guess that there is going to be gamma radiation. Because of this being able to go through the lead. And then last thing is, you can either say that there is beta radiation or there is no beta radiation. Doesn't really matter which one. You just have to give a reason for why you think so. So you can say that, well, it's able to go through thin metal, so it can be beta, or the metal is too thick. Beta particles will not be able to go through this metal, so it cannot be beta. So either is beta, or beta is present because beta is able to go through thin metal, or is not beta because beta cannot penetrate metal, or is stopped by metal. It's not important which one you choose. The more important part is that you explain why you think so. Part D, another radioactive source consists of a nuclide of cesium 137 that decays into barium 137. Write down the decay for this reaction. So you start with cesium, which is 137 and 55 protons. It decays into barium, also 137 and 56. Now, the number of nucleons is the same, so it must be beta decay. The charge has to be the same before and after, so it has to be electron with a negative charge. And if you have an electron, you have to have an anti-lepton as well, which is the anti-electron neutrino. Number 6. An experiment to investigate simple harmonic motion consists of a mass oscillating at the end of a vertical spring. The mass oscillates vertically above a motion sensor that measures the speed of the mass. Test 1 is carried out with a mass of 1 kilogram and a spring of a spring constant K, sub 1. Test 2 is a repeat of the experiment with a 4 kilogram mass and a spring constant K, sub 2. So let's go down. The variation with time of the vertical speed of the masses for one cycle of oscillation is shown for each test. So you have test 1 and this short dotted line, and test 2 and the other longer stroke dotted line. Speed is in the y-axis in meters per second, and time is in the x-axis. Part 1, calculate the frequency for the oscillations for both tests. To get the frequency, we'll get the period. The period in both cases is 0.8 seconds. So we'll go down, write that down. Period is equal to 0.8 seconds. The frequency is 1 over 0.8 seconds, which means the period must be around 1.3 hertz. Two significant figures. Part 2, it asks us to deduce K1 over K2, these two spring constants. So first, the use of the spring constant is in the equation the force is equal to spring constant times displacement. Also, acceleration is spring constant over the mass times the displacement. And if you think of it this way, angular velocity squared is, yes, spring constant over the mass. Now, in both cases, we found that the angular velocity or the frequency is the same. This means that the spring constant in both cases is proportional to the mass. Okay. That means mass 1 over the spring constant 1 is equal to mass 2 over the spring constant 2. That means the ratio K1 over K2 would equal to, again, mass 1 over mass 2. And this is 1 kilogram over 4 kilograms, so the answer is 1 over 4. Part 3, it asks us to determine the amplitude of oscillations for test 1. So, if you look at the graph, what we need is the maximum velocity. So we'll go back to the graph. In test 1, the maximum velocity is 4.8 meters per second. So let's use that, which is 4.8 meters per second. And the reason we use the maximum velocity is because the maximum velocity should equal to the angular velocity times the amplitude. And we know the angular velocity, because the angular velocity is 2 pi times the frequency. Therefore, the amplitude, which is the maximum velocity over the angular velocity, would equal to 4.8 divided by 2 pi times 1.3. And this simply gives us approximately 0.61. As a side note, you could also use 2 pi over the period, which means it would be 2 pi times the period of 0.8. And it gives us the same result. In part 4, it says that in test 2, the maximum elastic potential energy stored in the spring is 44 joules. When the time equals 0, the value of the potential energy for test 2 is 0. Sketch on the axis the variation with time of the elastic potential energy for test 2. So first, we start at 0 elastic potential energy because it says that it should be 0, that's equals 0. And in one full oscillation, you'll go back to 0. But here's the thing. If you look at during one oscillation, you get, if you look at the velocity graphs, something like this. Actually, let's not put it to scale yet. At the maximum velocity, you have 0 potential energy. But when the velocity is 0, you should have a maximum potential energy of 44. So let's go to 44. Put it here. And when the velocity is a maximum, again, you should go to 0. When velocity is 0, you should get to the maximum potential energy again. So again, another point here, and another point here. So you have to connect all these points. It's going to be sinusoidal. It looks kind of like this now. So what do you get from this? The energy graph does not have a negative side because potential energy is not negative in this case. It goes from 0 to maximum. Second, even though the period for the oscillations is 0.8 seconds, for the energy it's only half as much because it corresponds to the, if you see the displacement goes something like that. Positive displacement, you have positive potential energy. Negative displacement is still positive. For part B of this question, the motion sensor operates by detecting the sound waves reflected from the base of the mass. The sensor compares the frequency detected with the frequency emitted when the signal returns. The sound frequency emitted by the sensor is 35 kilohertz. The speed of sound is 340 meters per second. Determine the maximum frequency change detected by the sensor for test 2. So, number 1, first you have the source sending a sound that arrives at the mass. So the mass moving would be moving observer. So the change in the new frequency would be the initial frequency times the velocity speed of sound plus or minus the velocity of the observer over the speed of sound. Okay, what about after it bounces off? Now it's the mass that is the source and it's the moving source. So if the source is moving, it's this frequency that it received. So prime times the velocity speed of sound over speed of sound plus or minus the speed of the observer. So if you combine these two equations, you get that the frequency received is the original frequency. And if they're moving towards each other, at the maximum velocity is plus speed of sound minus speed of sound, like so. Oh, sorry, speed of sound plus speed of the object over the speed of sound minus speed of the object. It's been moving towards. This would be a higher frequency. So this is a maximum. And the minimum occurs when they're moving away from each other. It's the original frequency times velocity of sound minus velocity of the object over speed of sound plus the velocity of the object. If you look at the graphs reads that in test 2, the velocity would be at a maximum of 9.4 meters per second. This is the velocity of the mass, so we're going to use U0. Using these values here, you get that it would be 37 kilohertz. And if you assume it's moving away, you would get 33 kilohertz. So the maximum frequency change would be 2 kilohertz in both cases. So this is plus 2 kilohertz. In this case, it's also minus 2 kilohertz, but it's still 2 kilohertz. In question number 7, a metal sphere is charged positively and placed far away from other charged objects. The electric potential at a point on the surface of the sphere is 53.9 kilovolts. Outline what is meant by electric potential at a point. So, it is the work done per unit charge and you get this from the definition of potential, work per charge. But it's the work done when you bring a small point positive charge. From infinity to the point. So basically, it's the area under the field graph. Part B. The electric potential at a point at a distance 2.8 from the center of the sphere is 7.71 kilovolts. Determine the radius of the sphere. First, the voltage times the distance is some constant value. The reason for this is because voltage is K Coulomb constant, the charge over the radius. If you multiply this and this, you get Coulomb constant times the charge, which is taken to be approximately constant. What we will do is we'll use the value of 53.9 kilovolts here. So 53.9 kilovolts times whatever the radius of the sphere is should equal to the 7.71 kilovolts times the distance of 2.8 meters. This means the radius of the sphere should be approximately 0.40 meters. There's a second way to find this answer. So if you don't want to use this method here, which we'll delete, let's just start with the voltage being the Coulomb constant times the charge over the radius. So So Q1, let's put radius of the sphere. And the voltage would be the voltage at the surface of the sphere. Then the voltage some other points. So let's put just a point P, Coulomb constant times the charge, which is the same charge Q1, over the other distance. Let's use distance D here. And the answer will be the same. You just have two different equations. You put K Q1 is equal to the volume, the voltage of the sphere, times the radius of the sphere. And it turns out, in the end, it's the same result. This would still be equal to the voltage at point P times the distance at D, and you will still get the radius of the sphere as being 0.40 meters. Next, for part C, a small positively charged object moves towards the center of a metal sphere. When the object is 2.8 meters from the center of the sphere, its speed is 3.1 meters per second. The mass of the object is 0.14 grams, and the charge is 2.4 times 10 to the negative 8 coulombs. Comment on the angle at which the object meets equipotential surfaces around the sphere. So it's moving towards the center, and it's a circular object. Then the equipotential lines are all radial, which means it meets at a 90 degrees angle. Question number 2. It says, show that the kinetic energy of the object is about 0.7 millijoules. We're just going to use kinetic energy equal to 1/2 mass times the velocity squared. The mass is 0.14 times 10 to the negative 3 kilograms. And you multiply this by the velocity of 3.1 squared. You would get approximately 0.67 times 10 to the negative 3 joules, which is 0.67 millijoules as required. Part 3, determine whether the object will reach the surface of the sphere. So, you need a certain amount of energy to reach the surface of the sphere, which is the change in potential. So, the energy required is the charge times the change in potential, which is the charge of 2.4 times 10 to the negative 8 coulombs, and the change of potential would be the 53.9 kilovolts minus the 7.71 kilovolts. Using this, the energy required would be about 1.11 times 10 to the negative 3 joules, which is 1.11 millijoules. So you need more energy than there's kinetic energy. So the required energy is greater than the kinetic energy. So it will not reach the sphere. Question number 8. A fixed horizontal coil is connected to an ideal voltmeter. A bar magnet is released from rest so that it falls vertically through the coil along the central axis of the coil. So there's a bar magnet and it falls to the coil. The variation with time t of the EMF induced in the coil is shown. So we have the induced EMF in millivolts. Part A, number 1, write down the maximum magnitude of the rate of change of flux linked with the coil. Now, rate of change of flux is delta flux over delta time. This is the EMF induced in the coil. So if you want us to get the maximum magnitude of such, you have to go back to the graph. So we have 3 here, but it is about 5 times 10 to the negative 3 volts here. So this would be 5 times, where's that 5.0, times 10 to the negative 3 volts, which is the rate of change of flux. Part 2 says, state the fundamental units for your answer in A. Well, the units were volts, but it's not the fundamental SI units. This is equivalent to joules per coulomb. Coulombs are not fundamental. Amperes are the fundamental units, which is amperes times seconds is equal to coulombs. And joules are kilograms meters squared per second squared. So simplifying this, we get kilograms times meters squared divided by amperes and seconds cubed. In part B, number 1, says explain why the graph becomes negative. First, the flux is equal to negative n times the rate of change of flux. So as the bar gets closer, flux increases. But later, as the bar moves away, the flux decreases. As the bar moves away, the flux decreases. Which means the change in flux is in the opposite direction. So increasing flux, it has a positive sign. Decreasing flux has a negative sign, which means the EMF would also change directions. So change in flux is changes signs. So the induced EMF also changes signs. What does this mean? Well, remember that it's all related to Lenz's law. So we can also refer to Lenz's law for this. Lenz's law says that the induced EMF will be such as to oppose the rate of change of flux I created. So if the flux is increasing, it will be one direction. If the flux is decreasing, it will be the opposite direction. So as it comes closer, positive. As it goes through and the flux decreases, then it's going to become negative. In part 2, part of the graph is above the t time axis and part of it is below the time axis. Outline why the areas between the time axis and the curve for these two parts are likely to be the same. So first, the area represents the total change in flux. So what does that mean? Well, recall that area is more like akin to multiplication if you're thinking of an equation. So if the y-axis is the EMF, which is the rate of change of flux, and the x-axis, so let's write it down, is time. The area is multiplication. Imagine what will happen if you multiply time and the change of flux over the change in time. You just simply get the change in flux. Now, you should not write this as part of your answer. This is just an explanation so you know why this first statement is true. So, as the magnet approaches, the flux increases, and it will increase equal to the area. When it leaves, the flux will go back to 0, so the decrease is the same. So if you increase by 10 farads, you will decrease by 10 farads as well. Oh, sorry, Webers, because flux is in Webers. So as the magnet approaches, flux will increase by an amount. Or by a specific quantity. So when it moves away, it will decrease by that same quantity. And finally, part C, it says, predict the changes to the graph when the magnet is dropped from a lower height. If it's a lower height, the velocity will be smaller. This means the change in flux will be smaller as well. And since the EMF induced is proportional to the change in flux, rate of change in flux, so the EMF peaks will also be smaller. But the areas will be the same. Question number 9. In an experiment, a beam of electrons with energy of 440 megaelectronvolts are incident on oxygen-16. The variation with scattering angle of the relative intensity of the scattered electrons is shown. So there's the relative intensity of scattered electrons with angle. Part 1 says identify a property of electrons demonstrated by this experiment. Well, if we look at the graph, there is no reason we can discern that a particle would have this dip here. But if it's a wave, this would be the first minimum. So you're actually seeing the wave properties of the electron. It's just a one-point question, so you don't have to really say why, but if you ask why, it's shown because only waves can diffract, and there's a first minimum, so it must be diffracting. Part 2, it says, show that the energy of each electron in the beam is about 7 times 10 to the negative 11 joules. So energy is equal to the charge times the potential difference. the charge is 1.6 times 10 to the negative 19 coulombs, and the potential is 440 times 10 to the 6 volts. Multiplying this together, you get 7.0 times 10 to the negative 11 joules. Part 3. The de Broglie wavelength for an electron is given by Planck constant multiplied by the speed of light divided by the energy. Show that the diameter for an oxygen-16 nucleus is about 4 femtometers. First of all, you have to find the actual wavelength of the electron. And you can use either joules. If you use joules, you have to use the Planck constant in joules times the speed of light in meters per second divided by the energy in joules, which would be, in this case, approximately 2.8 times 10 to the negative 15 meters. Now, easier way to do this is also you can use the energy in mega electron volts and the Planck constant times the speed of light in mega electron volts or in electron volts as given in the physics booklet. Second, we have sine of the angle to the first minimum is equal to lambda over b. Usually this is b, this width of the slit, in this case is the diameter of the atom, nucleus. Second, we cannot use the small angle approximation. Notice if you go to the graph, the angle of the first minimum occurs at 46 degrees, and that means you cannot just use theta is equal to lambda over b. Second, because it's not in radians, it's in degrees. So you can find the diameter of the nucleus as being equal to the wavelength over the sine of 46 degrees. Wavelength is 2.8 times 10 to the negative 15, which gives us about 3.9 times 10 to the negative 15. And finally, in part B, it says estimate, using the results in the previous problem, this radius for oxygen-16, the volume of tin 118. Set your answer to an appropriate number of significant figures. First, you don't have an exact equation for the volume, but you have an equation for the radius of a nucleus. Use the Fermi radius times number of nuclei to the power of 1/3. Now, here's what happens. Every single nucleon will give us approximately this, adds exactly the same volume. So, if you go like that, the volume is equal to 4 over 3 pi r cubed, which is 4 over 3 pi for my radius cubed times the number of nucleons. The volume is proportional to the number of nucleons. So for oxygen-16, for O16, the volume is, well, it's half of this for the radius, first of all. So 4 over 3 for the volume times pi, and what is it? 3.9 times 10 to the negative 15 divided by 2 cubed. Next, if you find the volume here, you can calculate this right now, but if you want to find the volume of tin 118, so the volume of tin will be the volume of the oxygen 16, O16. And we divide this by 16, so you get the volume of one nucleon, and you multiply this by 118. So this is the volume of one nucleon, and there's 118 of them. Inputting these numbers, you should get approximately 2.4 times 10 to the negative 42 meters cubed, plus or minus 0.1. And that is it for today. Thank you for watching, and see you next time.